Now, welcome to this lecture on sequential circuits. We earlier had discussed digital circuits, but those were now that time a need has not arisen to tell them that these are combinational circuits, because when we are not exposed to next type, there is no need to name the first type. But now we are naming that type as first type because it is second type now. So, the circuits what we have discussed till now, various gates, their interconnections, then using K-map you have realized some Boolean equations, you have designed adders, half adder, full adder, subtractors, you had also designed gray to binary and binary to gray code converters. But in all these cases, what was the basic logic? Basic logic was there was unidirectional flow from left to right, in the sense that inputs were drawn from left and those were moving further, and the connections were allowed only from left to right, no connection from right to left, that is there was no reverse connection from any output to input of that gate or a previous gate. So, there is no concept of feedback for combinational circuits, or the circuits which are without feedback are called as combinational circuits. Now, that condition which was put, that not to have feedback, then one will ask, why should I put the condition, because everything is simple? No, now a time has arisen to lift that condition and we lift that condition. So, there is no more condition now and feedback is allowed. So, if feedback is allowed, we discuss various circuits, and the simple most circuit of that is we consider one OR gate, a single gate we can consider. A single OR gate we consider. To that we are having two inputs, input A, input B and output Y. It is an OR gate. I draw it very clearly again, an OR gate which has got two inputs and one output. Now, I want, using a single gate, the discussion which I am doing now is we want to break the condition which was put, that is no feedback. Now, we give feedback. So, how do we give feedback? Just have a connection from right to left, from output to input, and the simple connection what we do is like this. So, the question is, write down the truth table for this. In the truth table what you have got now? B's you locked it with Y, so only thing remains is A and Y. Only thing remains is A and Y. What will happen if A is equal to 0 and what will happen if A is equal to 1 is the discussion. Now, you can attempt this question, you can try to complete the truth table. From where you start? A wise person will start from A equal to 1. Why? Because for OR gate, logic 1 level is called as deterministic level, in the sense that if any input of an OR gate is logic 1, then output is 1 irrespective of other input. So, if A is 1, Y is 1. I think that is a simple question which you can answer. Y is 1. Now, so there is no need for you to look at B. So, you should not bother what is about B. But now, when A is equal to 0, what will happen? 0 is not deterministic state, means if one input 0, output depends on other input. So, for an OR gate, the level 1 is deterministic. It ignores other input and gives output as 1. And 0 is such that it is what we can say an excluding state. An excluding state means what? When an input is 0, output depends on other input as it is. So, if A is 0, what is Y? Y is B. For an OR gate, if A is 1, Y is 1, and if A is 0, Y is B, then you will write in the truth table Y equal to B. y equal to b. Right, so nothing wrong in it. But what is b? What is b? B is not independently connected, so I should not write b here. I will just write b here just to understanding purpose. B is not connected anywhere out from outside. So b is connected from y. So what is b? Because of gate, when a is 0, y is b. Due to gate, when a is 0, y is b. But due to direct feedback, b equal to y. Due to gate at a equal to 0, y is equal to b. And because of direct feedback, direct reverse connection, b is y. So you will rub out this b and you will write as y. And you will say, oh yes, my truth table is over. So what does it mean? Y is equal to y. How can it be truth table? It is just like, suppose if the question is asked in the examination, write down the description. Then you write down the question again, have an arrow and say, it means what it is. So what it is cannot be an answer to be written in the answer book. Right? Describe the principle of, say, thermocouple. The answer is, principle of thermocouple is, what is principle of thermocouple? So it is syntactically correct, but attemptively wrong. So y equal to y doesn't look good. But what is that? What y equal to y tells us? Y equal to y is actually in Boolean algebra is what we can say a non-conclusive state. You cannot conclude from y equal to y. Means what? If y is equal to 0, it will be 0. If y is equal to 1, it will remain 1. So it can be either 0 or 1. For both cases, y equal to y will be satisfied. So output is, if output is 0, still okay. If output is 1, still okay. In both cases, it will be satisfied. You start with 0, you end with 0. You start with 1, you end with 1. Now here if you start with 0, you end with 1. Then you are very much familiar with multiple choice questions. So when you are familiar with multiple choice questions, if you don't know the answer or if you can't find the answer, what you say? You check for various options, is it correct answer? So now like that, if truth table is to be found out, then you can start, you don't know the answer. You can start with the answer and check. Suppose if you put 0 here, a is 1, y is 0, b is 0, 0 and 1, 0 is a wrong answer and you will end up with 1. But if you start with 0, for a equal to 0, a 0, y 0. So y 0 comes here, 0, 0, 0. A 0, y 0, so b 0. So a 0, b 0, y 0. If you start with y equal to 1, y equal to 1, y equal to 1, a is equal to 0, y equal to 1, b equal to 1, a 0, b 1, y 1, a 0, b 1, y 1. So what you can have? Now a situation has arisen where for single input combination there are two output possibilities which has never arisen until now. In case of combination circuits, any input, any output is having a unique state for given input. Multiple input states may lead to same output. So for an, say, AND gate, if A is 0, B is 0, Y is 0. If A is 0, B is 1, Y is 0. If A is 1, B is 0, Y is 0. Sorry, A 0, B 0, Y 0, A 0, B 1, Y 0, A 1, B 0, Y 0, A 1, B 1, Y 1. So for 3 input combination, output is 0. And for one input combination, output is 1. So in combinational circuits, it was a situation that for multiple input combinations, there can be common output state, but for given input combination there can be two output states. That is now violated. So because of this feedback, every context of digital circuits analysis has changed, and for given single input combination there is a possibility that multiple output combination may hold good. How to work on this circuit, how to bring it to 0 state or how to bring it to 1 state, all these discussions which we can carry later on. That is actually, this is, you will not find this circuit anywhere except this discussion, because it is normally is not having any application. So you will not find this circuit, but if you ask me, then this is the circuit which we should go for, because this is the most important circuit. According to me, this is the most important circuit. So this is what we should attempt for, and this is the only circuit which will completely clear our fundamentals, that the very concept that a situation arises where multiple outputs are permissible. How they will occur is not a right now important question, but the circuit will satisfy itself, its working logic, for multiple output combinations for given input combination. So given input condition creates a situation where multiple outputs are possible for some input conditions. There are some input conditions which have fixed output. This is called as a sequential circuit, where I again repeat, this is very fundamental theme. What is I discuss all these things so as to create the final impression. What is the final impression? Sequential circuits allow multiple outputs. Output here there is no combination because there is only one, but multiple output combinations for same input combination. So there is one to many correspondence. In case of combination circuits, the correspondence was either 1 to 1 or many to 1, but 1 to many was not there. Here there is addition of 1 to many combinations for sequential circuit. So with this background now we proceed for most popular and most misunderstood sequential circuit, that is called as a flip-flop. So now we go for a flip-flop. It's very interesting circuit, and I am sure that I will try to explain it in simple words so that even if you decide not to understand, we are having a new concept of forced understanding. Means the bombarding is in such a manner that you cannot create a situation, you cannot create a condition where you will not understand. Flip-flop, so it is very interesting circuit. It uses NOR gates. It uses two NOR gates and cross coupling. A is input, B is input, C is output, and one output is C and other output is D. And now we write down a truth table. Obviously A, B, C and D. So inputs I write as zero, zero. Is it Readable? That's green ink. 0, 1, 1, 0 and 1, 1. So, there are 4 input combinations 0, 0, 0, 1, 1, 0 and 1, 1. Now, those who might have studied in standard 12th will try to attempt, but I am sure that they will attempt in the wrong manner. So, I would like to urge them to listen. So, how to start with it? Both are NOR gates. For NOR is OR and NOT. So, just like for an OR gate, for NOR gate also a logic input 1 is decisive state. Means if one input is 1, irrespective of other input, output will be 0. So, if A is 1, C is 0, if B is 1, D is 0, I am not required to check what is happening because of this somewhat complex cross coupling. So, A is 1, C is 0, B is 1, D is 0. So, wherever you find A is 1, put C equal to 0. A is 1 here, put C equal to 0, put C equal to 0. Wherever B is 1, put D equal to 0. Put D equal to 0, right? Now, so for this we got final answer, for this we have got partial answers, and this is something which we are unable to draw right now. Then, for this now, A is 1, C is 0, B is 0, A is 1, C is 0, B is 0. As C is 0, this other input is also 0. As C is 0, other input is also 0, B is 0. We are discussing this state, A1, B0. So, A is 1 has made C 0, B is 0. As C is 0, this is 0. So, 0, 0. So, if both inputs are 0 for OR gate, output is 0, and for NOR gate, output is 1. So, output is 0 and D. So, what is the future of D now? Listen again very carefully. B is 0. Since C is 0, see B is 0. C has become 0. As C has become 0, other input of lower NOR gate has become 0. So, 0, 0, 1. So, it is 1. In this case, as B is 0, D is 0. A is 0. As D is 0, this is 0. So, 0, 0, C is 1. So, all 3 combinations we have been successful in calculating. Now, the very interesting state A0 and B0. So, when A0 and B0, when A is 0, what is C? C is, it is NOR gate. So, when A is 0, output of OR gate is other input, and output of NOR gate is complement of other input. Are you getting me? For an OR gate, if one input is 0, output is other input for OR, and for NOR, if one input is 0, output is complement of other input. So, when A is 0, you cannot now comment on C. Here we could, because we were knowing other input. So, in these 2 cases we resolved, because at least one of them was in decisive state. Because of that, one output is computed, and because one output is computed, based on that other we could compute. But now, since both are 0, on its own it does not compute any input. And as no output is computed on its own, we can't proceed. So, we have to depend upon other output, that is interdependency. See how interdependency is. If A is 0, this is D. So I can write this as D here. Is there any harm? No. Is there any harm? No, right? So just I have written C has come here. So when A is 0, C is what? D bar, not D. Why D bar? Because it's NOR gate. So C is D bar. And what is D? When B is 0, when B is 0, D is C bar. D is C bar. So again, there is no unique answer. So C is D bar and D is C bar. Means what does it permit me? So here in this case you got answer for C, you got answer for D. But here now you have not got answer. The answer is D is C bar. It means C is D bar. Right? So how many variables are there? 2 variables. How many equations? 2 equations. C is D bar and D is C bar. But these are not 2 equations. These are same equations. So only 1 equation. If you think of 2 variables and simultaneous equations, then in that case, if 2 equations are same equations, that is x equal to 2y and 2x equal to 4y, these are not 2 equations, these are same equations. So like that, C is D bar, C is D bar, C equal to D bar. If I complement both of them, then I get D equal to, if I complement both of them, I get C bar equal to D. That means D equal to C bar. So 2 variables, 1 equation, not 2 equations because it is same equation. So if number of equations are less than number of variables, what does it conclude? Multiple solutions. So x equal to 2y, infinite solutions, it's a line. If x equal to 2y means if y equal to 3, x equal to 6, y equal to 4, x equal to 8. Many sets can satisfy that equation. So in Boolean algebra, that is simple. In case of continuous equations, there are infinite solutions. In case of Boolean algebra, not infinite, there are multiple solutions because C can be either 0 or 1. So when there is one equation and 2 unknowns, you assume one, you get the other. You assume one, you get the other. If you assume C equal to 0, then what is D? If C equal to 0, D is equal to 1. If you assume C equal to 1, D is equal to 0. So there are 2 solutions. So 2 solutions are either 0, 1 or 1, 0. I am rewriting again very clearly with bold and different color. 0, 1 and 1, 0. So in the same truth table, in the same row, I am writing 2 answers because both are possible and we will verify that. So either this or this. So let us start with this 0, 1. Let's start with 0, 1. What will happen? If D is 1, this is 1. A 0, B 0. D 1. As D is 1, this one will come here, it will make C 0. So if you start with 0, 1, you end with 0, 1. If you start with C equal to 0 and D equal to 1, D equal to 1 makes C equal to 0. And C equal to 0 and B equal to 0 make D equal to 1. If you start with 1, 0, in that case what will happen? As C is 1, this will become 1. As C is 1, this becomes 1. So once one input becomes 1, output will become 0. So if C equal to 1, that makes D equal to 0. And D equal to 0 and A equal to 0 makes C equal to 0. So these 2 are only possibilities. These 2 are only possibilities. Right? Now, then you will say, why 2? I suppose there is one kind of tendency of some rebellion. Then what kind of rebellion one can have? I will assume that how many outputs are there? 2 outputs. So how many possibilities total? 4. 0, 0, 0, 1, 1, 0, 1, 1. So I said that 0 is all right, 1, 0 is all right. Then somebody of you by some mischief may stand up and say, sir, I will start with 0, 0, let us see what happens. I will start with 0, 0, let us see what happens. Or I will start with 1, 1, let us see what happens. Then what will happen? Both states are not allowed, means they can't continue, they can't sustain. Because if, let us, since you say we make both 0, what will happen? We make both 0, what will happen? Let's assume that both are 0. So both are 0 means now what happens? Just it is a very interesting discussion. Both 0 means this is 0 and this is 0. So what will happen now? We started with both 0. We started with both zeros. So both inputs A and B are 0. We assume both outputs are 0. Assume both outputs are 0. What will happen? Both outputs 0 will get reverse feedback. So both gates will have both inputs as zeros. So when both inputs are 0, what is the output for OR gate? 0, and for NOR gate 1. So if both inputs are 0, output is 1. So if this is 0, this is 0, this is 0, this is 0. So this 0, this 0, A is 0, we also write again here, A is 0 and B is 0. We start with C0 and D0. C0 will try to make D1. Why? Because B is 0. C0 will try to make D1. And what D equal to 0 does? D equal to 0 will try to make C1. See now, it is self-destroying state. 0, 0 state is self-destroying. Means what? 0, 0 state is self-destroying. Means C equal to 0 wants that D should be made 1. D equal to 0 wants that C should be made 1. What will happen? Out of these two, which gate is fast? That will become 1. So if this gate is fast, this will become 1 first. And the moment at which it becomes 1, what C was doing? C was trying to make D1. D was trying to make C1 because both were 0. C equal to 0 was trying to make D equal to 1 and D equal to 0 was trying to make C equal to 1. Now this became 1 first. The moment at which it becomes 1, it will go here and it will maintain C equal to 0. C equal to 0 was trying to make D equal to 1 and D equal to 0, as until the point D was 0, it was trying to make C equal to 1. But D has become 1, D succeeded, D was fast. So it became 1, it will remain 1 and it will make or it will force C to be 0. So when one gate becomes 1, the other gate will remain 0. If this gate is faster, what will happen? If this gate is faster, C will become 1 because this D was 0 means till the time both compete, and when C becomes 0, when C becomes 0, when C becomes 1, this 1 will come here and this D will remain 0. So both gates try to become 1 and whichever gate becomes 1 first, other gate will remain 0. So 0, 0 state will self-destroy into either 0, 1 or 1, 0. 0, 0 is self-destroying state, not a stable state. It is called as state transition diagram. It will go to either 0 1 or 1 0. Now we start with 1 1 state. We start with 1 1 state. So what will happen? 1 1 is also self-destroying state, because C equal to 1 will make D equal to 0 and D equal to 1 will make C equal to 0. So whichever gate is faster, C is 1, that 1 will come here, D is 1, that 1 will come here. So this one will try to make this 0, this one will try to make this 0. Whosoever reaches 0 first, if this reaches 0 first, this 0 will come here and this will remain 1. So 1 1 will also self-destroy to either 0 1 or 1 0. Now this is called as state transition diagram. It's, even though it's somewhat complex, but I tried my level best to explain in simple words. So for input A equal to 0 and B equal to 0, what are the outputs? Outputs are either 0 1 or 1 0. These are stable states. They remain there. They remain there. State 0 0 or state 1 1. What happens? There is no, this arrow means stable state. If you think of some kind of logic like Hindu mythology, that is birth, death and moksha. So these are moksha states, salvation. So they remain there as it is, they don't change, both are stable states. But the 0 0, 0 0 can't remain. 0 0 has to self-destroy into either 0 1 or 1 0. Same is with 1 1. Same is with 1 1. Right. Now, the state transition diagram is for C and D, but C and D are outputs. These are, the state transition diagram is if it is in one state, whether it will remain or it will move away, is the situation. Now, how this state means, this is state transition diagram for A equal to 0 and B equal to 0. For A equal to 0 and B equal to 0, this is the diagram. Means when A and B both are 0 0, if this state is 0 1, it will remain 0 1. If this state is 1 0, it will remain 1 0. If means when A and B are 0 0, when A and B became 0 0, that time what were C and D? If C and D were 0 0 1, they will remain 0 1. If C and D were 1 0, they will remain 1 0. If C and D were 0 0, they will either move to 0 1 or 1 0. If C and D were 1 1, again same thing will occur. Now, I again repeat, it's not so easy, it's quite interesting. This is state transition diagram of flip-flop or this sequential circuit. This is for these three combinations, no discussion. This is a state transition diagram of C and D for A and B to be 0 0. For A and B to be 0 0, this is the diagram. Means when A and B became 0, now you came to class, it's virtual class actually, you came to class, but from where you came to class? Is it that somebody took birth in the classroom? No. So you came to class, we exclude the transition, that is, then when we say I came into the class from the door, that is obvious, that is a not meaningful answer. I came to the class through corridor, it is a not meaningful answer. Means corridor and door is transit way. Prior to that, you were in the room. So you came to class from the room, or you came to class from canteen, or you came to class from playground. So when you came to class, Prior to that you were somewhere. Prior to that you were somewhere. This is a state transition diagram of C and D for A and B to be 0, 0. Right. Now, before A and B were 0, 0, A and B means now you come to classroom. Let us define that normally a student is there in hostel room, canteen and ground and classroom, right. So, in classroom he comes from three cases, either hostel or canteen or playground. So, this is state transition diagram of A equal to 0 and B equal to 0, 0. So, AB equal to 0, 0 can come from, how I can, this is classroom, this is, I am giving simple example, this is classroom. Let us say this is hostel room, this is canteen, and this is a very simple example I am taking. So, what matters? If you come from hostel room in the classroom, it is expected that you have studied well and you will listen and understand well. If you come from canteen, chances are less. If you come from playground, chances are further less. So, you are in the classroom, input state is classroom, but previous input state was one of these three. So, if your current input state is 0, 0, the question is what will be the current output state? What will be the current output state? So, if your current input state 0, 0, you come from hostel to classroom, what was previous input state? 0, 1. That time what was previous output state? 1, 0. So, prior to AB equal to 0, 0, A and B were 0, 1. When A and B were 0, 1, C and D were 1, 0. So, prior to this, so if you come from 0, 1 state of A and B, that time when A and B were 0, 1, where were C and D? C and D were here. And it is seen C and D were here, and if C and D were here, now you come to classroom from hostel, so A and B has become 0, 0. So, if you move from A0, B1 to A0, B0, when A was 1 and B was 0, C was 1 and D was 0, when A and B become 0, 0, the state transition diagram is 1, 0 is a stable state, so that state will remain. That state will remain. You were here prior to AB 0, 0, AB was 0, 1, so CD was this and CD will remain this. If previous state was 1, 0, what will happen? If previous state was 1, 0 of A and B, what was state of C and D? It was this. And now what you are doing? You are moving from here to here. So, you are moving from AB equal to 0, 1 to 0, 0, last state will remain. From AB 0, 1, you are moving here, last CD was 0, 1, that will remain. Now, a very interesting situation. A1 and B1, you are coming from playground. When you were in the playground, what was the last state? Last state was 0, 0. And now, when you move AB equal to 0, means when you come to A equal to 0, B equal to 0, from A equal to 1 and B equal to 1, the last state was 0, 0. In previous two cases, last state was 1, 0 and 0, 1, they continued. Now, last state was 0, 0. Now, what will happen? the moment at which A equal to 0 and B equal to 0, this state can't remain. These were states which were remaining. This can't remain. So, you don't know where you will end up. So, if last state was 0, 1, when for A equal to 0 and B equal to 0, if last output state was 0, 1, that will be maintained. If last output state was 1, 0, that will be maintained. If last output state was 0, 0, that will not be maintained, and where I will end up, I can't predict. I can't predict. So, this is the situation, and this is something which means this is a state which you can achieve for some other input combination. This is a state which you can achieve fixed for some other input combination. So, these three states are for these three input combinations, right? There are four states for C and D, 0, 1, 1, 0, 0, 0, 1, 1. So, this state is there for this input combination, fixed state. This state is there for this input combination. This state is there for this input combination. And this state is there, but there is no input combination which will make this state. This is an impossible state if A and B are 0, 0. But this is a perfectly possible state when A and B were 1, 1. These are the possible states when A and B are 1, 0, A and B are 1, when A and B are 1, 0, C and D are 0, 1. When A and B are 0, 1, C and D are 1, 0. So, these three fixed, now here there is no option, there is only one output. So, these three are unique output cases, unique output input combinations. So, there are 4 input combinations. For 3 input combinations, we get 3 unique outputs, and for this combination, we can have 2 outputs. This output we can't get for any input combination. It can't remain also, and it can be obtained also for any other input combination. I repeat, this 0, 1, the C equal to 0 and D equal to 1 can remain if A is equal to 0 and B equal to 0, and it can be obtained for A equal to 1 and B equal to 0. C equal to 1 and D equal to 0 can remain for A equal to 0 and B equal to 0, and it can be obtained for A equal to 0 and B equal to 1. C equal to 0 and D equal to 0 can be obtained for A equal to 1 and B equal to 1, but it can't remain for A equal to 0 and B equal to 0, it will go either way. C equal to 1 and D equal to 1 can't remain for A equal to 0 and B equal to 0, and it can be obtained also for any other combination. So, we remove that. It is a meaningless combination, but this is a meaningful combination. So, if last state is 1, 0, that will be maintained. If last state is 0, 1, that will be maintained. If last state is 0, 0, I can't say anything here. It can be either this or this. Therefore, now, if we decide that we will not allow this input combination to occur, that is called as forbidden. Forbidden is an English word which normally Marathi medium students don't understand so appropriately. So, instead of forbidden, it should be banned. In fact, it is boycotted, but banned is a proper word. If this input combination is banned, then this output will not occur. If you read some what we can say substandard material, then you will say that race occurs here. Race doesn't occur at all. If A is 1 and B is 1, race doesn't occur. C is 0 and D is 0. When race occurs, if I move from 1, 1 input state to 0, 0 input state, I can't predict what the output will be. There is a race. If I move from here to here, the race is either here or here. So, if previous input state is 1, 1, previous output state is 0, 0, if I make input as 1, 1, I can't predict what the output will be, and therefore, if I decide that this is to be banned, if this is to be banned, then what are the remaining states? 0, 1, that will remain, continue. Means if A was 1 and B was 0, that time C was 0 and D was 1. If I now make A equal to 0, so 0, 0, that 0 will continue. If A was 1 and B was 0, outputs were C was 1 and D was 0. Now if I make B equal to 0, that will continue. So if I decide that this is band, then the 0, 0 for this I write as last state. I write as last state. Means there is not unique state. There is no unique answer in the truth table for A equal to 0 and B equal to 0. There is no unique answer. There are two possibilities, either 0, 1 or 1, 0, depending upon how you came to 0, 0. If you come from canteen, you would be in casual mood. If you come from hostel, you are maybe in serious mood. So in the classroom, what you do? You continue the mood from where you have come. So if from 1, 0, if we move to 0, 0, outputs will remain 0, 1. If from 0, 1 I move to 0, 0, outputs will remain 1, 0. And if I attempt to come from 1, 1 to 0, 0, outputs were 0, 0, that will not remain. I can't predict the outputs are. So this last state I can write if and only if this is a band state. So the meaning writing last state is permitted if this state is band. If this state is not band, you can't write last state. So unless you write band here, you can't write last state here. In many substandard books you find band, or in classical words you use the word forbidden. Unless this state is forbidden, you can't write. So in some truth tables they write forbidden here in the output column. In the output column, forbidden is not to be written. Outputs are well defined 0, 0. Or in some books you might have found question mark, as if something can't be found out. It is not like that. When A is equal to 1 and B is equal to 1, C is equal to 0 and D is equal to 0, it is perfectly stable state. If we decide to, this is not something unstable, this is not something unpredictable, this is not something which is race. If we decide not to use this state, then we can write last state here. Then now in some literature you will now find this flip-flop terminology as this C is marked as Q and this is marked as Q bar. This is because this is not allowed. Means Q and Q bar you can name. In some books, maybe a few years back, you say that Q and Q bar both can't become 0. As if the flip-flop understands that names are given as Q and Q bar. So it is just ridiculous logic. If this is band state, then we can write Q and Q bar. If this is band state, we can write Q and Q bar. But if this is allowed state, then both will become 0. Means Q and Q bar are names given for our simplicity in understanding, and we are not using this state. If this state is not used, then meanings of Q and Q bar are meaningful. And this is called as S, this is called as R. So this is R, S, Q and Q bar. Or to be rather, what is, I think this convention has been established few years back, maybe 5, 6 decades back. There is a mistake. They should not have given the word Q bar. If you ask me what the name should have been given, Q dash. Q and Q dash. Q dash is normally Q bar. In permissible case, Q dash is Q bar. And in exceptional case, Q dash equal to Q. So if you ask me, the name should have been Q dash. Q dash is our name, and or I write Q dash here and Q bar standard. We can't change the world convention. So Q bar, but for our understanding it is Q dash. So when R equal to 1, R is resetting. R equal to 1 makes Q equal to 0. S equal to 1 makes Q equal to 1. So S equal to 1 sets the flip-flop. R equal to 1 resets the flip-flop. S equal to 0 and R equal to 0 maintain previous state of the flip-flop, that is called as memory. So flip-flop can remember the previous state. So for these, now this is band state, we will not allow this. So when this is 0 1, from 0 1 when you go to 0 0, this previous memory continues. So this is called as means ability of sequential circuit to remember the state is called as memory. So this is simple SR flip-flop. Now there are multiple versions like D flip-flop, flip-flop with enable, flip-flop with clock, and JK flip-flop and counters. So in the next lecture we will go for the remaining flip-flops and then counters. I think it is too much heavy dose, it is better to stop now.